thought we were done, but it looks like we've got just one more problem to look at. Example 5. Ooh, this is actually a really good one. This is something you can probably see lots of times before. Okay, static equilibrium. So it's keeping everything in balance, nothing moving, just kind of like those two tension cables. You have a 100-kilogram TV is loaded into a trunk using a 30-degree ramp. We want to find the normal and the frictional forces on the TV if it is left sitting on the ramp. Okay, so we've basically, you draw yourself a picture and then you draw yourself more of a working picture per se. Okay, you've got this TV that's sitting here. It's got an X component and a Y component. You got the force being, then I guess the normal force is always, that's the N right here. The normal force is what's pushing up against. Like when you're standing on the ground, there's a force actually pushing against your feet, and that's always the normal force. And then you've got a force going this direction. Okay, and just like we did with the tension cables, you have everything in balance. The F force plus the normal force plus the weight has all got to balance out to a nice fancy 0. Okay, so let's work with this just a little bit more and see what we can come up with. Doing some math. Okay, well, the F vector, as you notice how we did, you see how we did an XY axis kind of off countered a little bit? If you look at the F vector, okay, and break it down just like what we did before in the last problem with T1 vector, T2 vector, and the weight vector, if we break it down, because this F vector is only going in the X direction, it only has a X unit value, and that's it. The normal vector, since it's only pushing up against it, it's only pushing in the Y direction, I guess you consider it as 0. Let's put it like this. It doesn't have an X portion, it only has a Y portion. Okay. The weight, now that, because it does act in directions, it's the one coming down right here, it does have an X and a Y portion of it. Because it's kind of coming to the left with respect to the X axis, then it's a negative 981 times the cosine and again, because it's down, it's also going to be negative for the Y. And just one second. Okay, I guess I'm getting way too excited that this is our last problem. It helps if I put degrees in. Instead of just writing the degree, that it would kind of help if I actually put it in. Okay, it didn't say something like 30 degrees, right? And then there's the I component. And then the Y component, again, it's 981 since we found up there, times the sine of 30 degrees. Okay, so if we kind of actually work this one out just a little bit more so we have numbers to work with. So negative 981 times the cosine of 30 degrees is going to give us a value of negative 800, and let me just go ahead and round it, so 850 times its unit vector. And if I do the same thing with the sine of negative 981 and the sine of 30 degrees, then we'll get it basically rounding as a negative 491 times its unit vector. Alright, and then to wrap this up, using this main equation right here, saying that this plus this, if we take that away since we rewrote it, plus this all has to add up to 0, then we basically, if we kind of write it out, all of the I components, so F plus there's 0 from the N1, and then minus 850, all of that times I, plus, and let's then do the Y component or the J component, the unit vectors. There's nothing from the F, so N minus 491, all that times J should equal 0. So the only way we can get that is then if F is 850 newtons and N is 491 newtons. Alrighty, and we have finished our last problem.